Okay, in this video we are going to solve two homework problems, and these are from Supplement C, which is about special inventory models. I recommend that when you're doing the homework, you open the slides for that particular chapter. So this is what we are doing, Supplement C, special inventory models, because the slides have the formulas you need, as well as solved examples which are similar to what the homework is asking you to do. So I'm going to, instead of just solving the problem, I'm going to refer to the slides. So I am in a way pretending to be a student, and I'm going to find the relevant information in the slides just to show you how you can easily do the homework, and actually the exams as well, because the exams are open the slides, so you can refer to the slides in an exam as well. So first up, we have to identify which problem it is. So if you read this problem, we have a university bookstore and we buy mechanical pencils. We get different quantity discounts. So if you buy a small quantity, you pay $4.10. If you buy medium quantity, you pay $3.50. If you buy a large quantity, 2001 or more, you pay the reduced price of $3.25. So this is obviously a quantity discount question. In Chapter 9 and Supplement C, which covered inventory management, we only did one type of problem where the price decreases the more you buy and what to do in that situation. So even without reading this part that we are being asked to find the order quantity, just this table and just the first line tells me that I am doing a problem about EOQ with quantity discounts, because there's nothing else we covered in inventory management that has the price decreasing as you buy more and more quantity. This is the only type of problem we did. Okay. So in this problem, we're going to have to find the total cost using this equation, and we basically have to follow these three steps to find the optimal quantity. Before we proceed, we're just going to double check that the question indeed is asking us for the optimal quantity. So we return to the question and read on. Annual demand is given, ordering cost is given, holding cost 30% of the unit's price is given. Determine the best order quantity. Best is a synonym for optimal. And so this is exactly what we have to do. So we just need to follow this process to get the problem done. In this problem, we use the standard EOQ formula to compute candidate solutions for different prices, and then we check them for feasibility and so on. But essentially, we're going to be computing, multiple EOQs for the different prices. So I like to put all the information in Excel. Okay, so I have three situations. I have the low price case, the medium price case, and the high price case. You always want to start with the lowest price. Okay, and it's not something I'm telling you now. The slides already tell you always start with the lowest price first. Why? Because if the lowest price solution is feasible, which you're going to see in a while what that means when I say the lowest price solution is feasible. What does that really mean? But if that is true, then you're done. You don't need to worry about the higher prices. But if it is not feasible, then you have to compute EOQ for the medium price and then for the higher price and so on. So the shortest and fastest way to solve the problem is to check the lowest price solution first. So lowest price, what is the price? I'm going to call it C, the cost of the item. Why? Because I know my holding cost, capital H, in dollars per unit per year is equal to small h times C. And the capital H, the holding cost in dollars per units per year, is used in the EOQ formula. And so the C is just how much money I pay to the supplier of the pencils, which is the price the supplier charges me. The price for the supplier is a cost for me because I have to pay that price, right? So that's my unit cost, C. 3.25. And then in the medium price case, the price goes up to 3.5, and in the high price case, the price goes up to 4.1. Okay, my holding cost as a percentage is 30%, no matter what the price is, right? So the question says 30%. Now remember, the numbers might be different for you, because when you do problems on the MyLab system, it can generate different numbers for each student, right? So the process of solving this will be the same, but the numbers, the actual numbers might be different. For example, the holding cost as a percentage, small h might just be 25% or 22% for you, something like that, right? Or these numbers might be different. In any case, I can use H and C to calculate capital H, the holding cost, capital H, which is dollars per unit per year, right? And this is just simply small h multiplied by small c. So I take 30% of the item cost and I get that. The good thing about making this table, okay, the good thing about making this table is I can simply drag this formula to the right and it'll apply to these values and these values. Again, if you don't know what I'm talking about dragging a formula, you should do the Excel tutorials that I've linked on Blackboard. On Blackboard, on the left menu area at the bottom, there is an Excel review option, okay? And if you go there, you have a bunch of Excel tutorials, knowledge you should know prior to this course, because you're supposed to have done statistics and business analytics / management science courses, right? SCM 313, SCM 212 in UM Flint. So those two courses are your Excel preparation courses, part of their objective, in addition to other things. And so you should be familiar and comfortable with Excel. If you're not, redo those courses or do the Excel tutorials that I've linked on Blackboard. You should have already done them in the first week of the course. Anyway, I go to the corner here and I drag the formula to the right and I get H for all three cases. Now let's put in the other data. Demand is just 2,400, annual demand in units. So D is, demand in units per year. For 1 year, what is the demand? Ordering cost S is $12. What else? That is all we need. And then we can plug in the EOQ formula. It's a square root of 2 times the demand. So I just select, I don't type in 2,400. I just select the cell with my demand and the ordering cost, right? And then you divide by H, okay? And so the economic order quantity, if the price is $3.25, is only $2.43. But there is a problem, okay, with this answer. What is the problem with this answer? If I look at my pricing table given in the question, if I'm ordering 243, or even if I go up to 244 because I have 243 and a fraction, even if I go to 244, where is 244 in this table? It's in the middle row. Because if you order 244 pencils from the wholesaler, he's going to charge you a price of 3.5. The 3.5 contradicts with the 3.25 because we assumed the price was 3.25. But when we go to the wholesaler and call up the wholesaler and say, I want to order 244 pencils or 243 pencils for a price of 3.25, the wholesaler is going to say no. Because that price is only available if you order 2001 or more. So that is called the problem. The solution, the EOQ, is not feasible. Okay, for this one. So because it's not feasible, I have to go on and calculate the EOQ for the medium price. Okay. So we'll do that. Now, I can just drag this formula to the right. It will automatically calculate EOQ, except that it refers to a cell 2 cells above it, and there's nothing here. So first I'm going to copy over all of these things, just repeat them, and then I can drag the EOQ formula and get EOQ for all of these options. Okay, now we got 234 as the EOQ for the medium price. Is that feasible? Yes, if you call up the wholesaler and say you want to order 234 pencils, the wholesaler will give you a price of 3.5, which is also the price we use to calculate this EOQ. So this is feasible. Okay. Okay, and then you can stop here and then just consider these two solutions. Now, I kind of missed a small step here. When you do get an infeasible solution, you do have to convert it to a feasible solution. So we have to move the quantity away from 243 in a direction that you hit the feasibility limit for this price. So what is the closest number to 243 that will give me the price of 3.25? 3.25. Well, 3.25 is available at 2001 or more. 2001 is the closest number in this range of 2001 and more. That is the closest number to 243. So I'm going to round up, okay, to 2001. Okay, 2001. And then this solution was feasible as is, so we'll stay at 243. And I don't need to test the high price solution because my rounded up solution, okay, so candidate solutions, and this one is just going to be the same one, right? My two candidate solutions right here, one of the two is going to be optimal. I don't have to check the high price one. Why? Because medium price gave me a feasible solution. If, for argument's sake, let's say the price of 3.5 only applied at 300 or more units, and this was also not feasible, then you would also look at this one, and 216 is feasible because this would be 0 to 300 in that case, and then you would have three candidate solutions, and you would round this up to 300 here. If you know it was 0 to 300 and 301 to 2000, you will round this up to 301. Right? So depending on the structure of the table and your numbers, you may have to round up certain solutions until you exhaust either all of the prices or you hit a feasible solution, and then you don't have to go to any higher price than that. So we have two candidate solutions. For each solution, we have to calculate, you know, holding cost, ordering cost, purchase cost, and the total cost, which is the sum of these three costs. So total cost is easy. Total cost is just this plus this plus this, right? Let me click here, plus this. B16, oh, this is going to be plus B14 plus B15. Let me actually do this. B14 plus B15 plus B16. Okay, that's going to be my total cost. And then I'm going to compare these two solutions, these candidate solutions, and see which one is optimal, right? So if you go back to your slides, you can see that if the quantity is too low, you have to round it up, just like we did here. We rounded up 243 to 2001 because 243 was too low for this price. And then if it is feasible, then that is the last candidate solution. And then we're going to compare all candidate solutions on total cost. This is the step we are doing now. Okay, so how do we get this cost stuff? Well, this is the cost formula. Okay, the first part of the cost formula, Q over 2 times H is your holding cost. The second term is your ordering cost. The third term is your purchase cost or procurement cost. And you add the three up to get C, which is your total cost. Okay, so holding cost is just Q, over, Q is the EOQ. So you take the EOQ quantity, divide it by 2, and multiply it by the relevant H, the holding cost in dollars per unit per year. And don't multiply by the small h, you have to multiply by the capital H. Okay, so that's your holding cost for this, and then you can just drag it over and you also get holding cost for the second solution. Then ordering cost is going to be capital D over the EOQ quantity Q times S. So you do capital D divided by the EOQ quantity. Notice we're going to use the candidate solution, not the one the EOQ formula gave us because we rounded it up. Have to use this value which you round up to get the cost for that value, because you're not going to get a 3.25 price at 243. Okay, so we do D over Q times the S, which is S is $12. Okay, and then you can just drag it to the right and do it for the second solution as well. Okay. And then purchase cost is just going to be the price times how many units you buy. Well, you're going to buy the 2,400 units because that's your demand. And so that's the purchase or procurement cost, and you do that. Okay, so your total cost is this and this. So 8789 is bigger than 8645. So you always go with the smaller number. And then this is your final answer, that your optimal solution is 234.216, quantity to order at a price of 3.5 for an annual total cost of this much. This is optimal. Okay, now just to check whether our algorithm works, we can also do the same thing here for a high price. Okay, we know that price of 410 is only valid from 0 to 200. It's not valid at 216. okay, this price. So we're going to have to move this down to 200, okay, so that we can use a price of 4.1. Why don't we move it down to 100? Because you have to move it down the smallest amount till this price becomes valid. So if you're at 216 and you start going down, as soon as you hit 200, you get the price that you assumed and you stop there, okay? And then if you calculate the total cost, okay, for this one, right? I want to take away the formatting. Okay. So if you calculate the total cost here, you'll see that for the high price, your total cost is higher than your optimal solution. You didn't have to do all this work because we knew if you go from low price towards the higher price, stepwise, when you get a feasible solution, you stop. You don't have to check out price higher than that, but you could, just to be safe, if you wanted to. I mean, it's mathematically proven that this algorithm works that I'm showing you on the slide. But if you wanted to, in Excel, it's just dragging some formula cells over, and you'll see that this is the lowest total cost. So this is your answer. Okay, so enter your response round to the nearest whole number. So when I round this to the nearest whole number, that's 234. You can also use this button in Excel to hide the decimals, and it gets rounded to the nearest integer. So it's 234. Okay, so that was that question. That question is done, right? This was the optimal order quantity. So let's do the second question now. The second question is asking us about a winter jacket that sells for $120 in the winter season. It costs us $70 to get the jacket from the supplier, and then we sell it for $120. Right? At least the retailer does, and unsold jackets are sold for $50 after the winter season is over. So if we have too much stuff that we purchased from the supplier and we're unable to sell all of our stock, the remaining pieces, they have to go on a clearance type of sale after winter is over, and we just get them out of our system, $50 a piece, and we actually lose money because we paid the supplier $70 and now we're selling them on $50 a piece, so we're losing $20 a piece on them. Demand is normally distributed with a mean of 2,500, standard deviation of 600. Replenishments cannot be ordered once the winter season starts due to long lead times, and we have to determine how much quantity to order. Now the key phrase is replenishments cannot be ordered. All of inventory management we have done in chapter 9, the continuous review system, the periodic review system, you reorder again and again and again. But when you cannot reorder, you cannot have a replenishment, that's a different class of problems, which we do in Supplement C, which are called one-period decisions. Right here, one-period decisions are all about when you have a short selling season as compared to the lead time and you cannot reorder. And it even gives you the example of a winter jacket in the slides right here, right? So we are in the right area to see how to solve this problem. Right. So these problems are pretty simple. You have to find CS, or cost of shortage per unit, cost of excess, and then you have to find this optimal service level, and then you can figure out from the probability distribution how much to order. Right. So let's do this problem. Okay, so we have to calculate CS, which is the cost of a shortage, CE, cost of an excess, and then our optimal service level. And you can also look at this example, right? There's just a winter jacket example in the slides, right? So how that would help you. You can just follow the same steps as this example. Okay, so what is the cost of a shortage? The cost of a shortage is when you have too few jackets and you're losing sales. So each time you lose a sale because you didn't have inventory, you could have earned $120 in revenue, right? Because you sell them for $120. And to have that extra jacket in stock, you would have paid $70. So you make $50 a piece when you sell a jacket, and you lose $50 if you have one quantity of a shortage of one piece, one jacket too few. So if you ordered 99 and demand is 100, you're one short, right? You're one less. And so that being that one less than the demand, you lost $50 of profit. Okay, excess is the opposite. Like you ordered 100 jackets and demand is 101, so you're short of one. Sorry, you ordered 100 jackets and demand is 99, and so you have one extra jacket. That's an excess. So if you have an extra jacket left over, you'll sell it for $50, but it costs you 70, so you're gonna lose $20 on that. So that's a cost of $20, and this is a lost profit, which is a cost. If you lose out on making money, that's like a cost, opportunity cost, kind of like an opportunity cost. So that's 50 and that's 20. So when we go back to the slides, when we have these two, the optimal service level is CS divided by CS plus CE. So we take our CS and we divide that by the sum of CS and CE, and that is 0.714. Okay, so what that means is that we want to have a probability of 0.71 that the demand will be less than equal to whatever quantity we order. So we will order Q star, some optimal quantity, such that demand demand does not exceed Q star. Okay, i.e. demand is less than equal to Q star with a probability of 0.71429, the optimal service level. That's what the optimal service level means, that you want to order a quantity so that demand is going to be less than equal to that quantity with the probability of that service level. Okay, so you might want to draw a picture to show you what's happening. Okay, and in the slides I show you a picture like that as well, or do I? Okay, maybe I did not draw a picture in the slide, so let's draw a picture here. Please give me the whiteboard. Okay, must have updated the whiteboard before it would start very quickly. Okay, finally we're in the whiteboard. So our demand has a normal probability distribution. It has a mean value. If you go to our question, the mean value is 2,500 units, so it is 2,500 units, right? And it has some standard deviation sigma, and that is 600, right? This is a 600. Okay, and so we want to order a quantity, okay, Q star, such that the probability of being equal to or less than Q star is 70%. So you're gonna be below on this side, this area that I'm shading, this shaded area, which is the probability, has to be 0.71. Ooh, why did I draw those arrows? Let me see if I can erase this. Okay, so 0.71. I did this. No arrow. Okay, so that's going to be your ratio that you call it, 0.71429. Okay, 0.71429. Okay, so given we know the probability distribution is normal, right, and we know the mean, the standard deviation, how can we calculate Q star? There's a very easy formula to go from probability to a quantity. It's the inverse formula, norm INV. Okay, and we can use this formula in Excel to do that. So our Q star will be norm.inv. Probability is this, 0.714. The mean is given in the question as 2,500. Standard deviation is given in the question as 600. And so we get 2839.57. Let's check the question for rounding instructions. Optimal service level, first of all. So this is the optimal service level. Down to 3 decimal places is going to be just 0.714. If you don't know how to round, just click this button until you have 3 decimal places being shown. Although hopefully you know how to round. And so it's 0.714. So Excel makes life really easy for us, right? We can round to whatever we want using these buttons. Okay, the optimal quantity to the nearest integer. Again, we're going to use Excel to round this for us, so we don't, get tired. So that's 2840. 2840, And let's check our answer. So we got it. Okay, we got it correct. Okay, so that's how you find Q star once you have the optimal service level. Now be warned that the slides show you that when the demand is normal, we use this norm.inv formula. However, if the demand is not normal, sometimes you're given a table like that. The demand is 10 with a probability of 0.2, demand is 20 with a probability of 0.1, and so forth. In that case, you have to calculate this cumulative probability column, and then you have to see where does your service level fall. So in this case, service level is 0.71. So 0.71 is between 0.5 and 0.75 in the cumulative column. And so you'll go with the quantity that corresponds to 0.75, the higher quantity, right? And, you know, I do an example in the slides, so refer to the example in the slides in the lecture video for more details on that. Okay, so in this video, we have successfully solved 2 homework problems. This is just to help you out, to show you how the slides are really beneficial to solve the problems and how setting up the problem in Excel makes everything super duper easy. So hopefully this was helpful, and that's it.